Hello and welcome to the second lesson in the second unit. We're looking at Newton's three laws of motion today. So what's the goal? I want you to be able to explain each of Newton's three laws, and then I want you to be able to apply them in real-world applications. So let's talk about Newton's first law, and you might know it as the law of inertia, but it is Newton's first law. And the textbook definition is an object at rest will continue at rest until a force is applied to it. An object which is moving will continue moving until a force is applied to it. So, definition first of all of inertia, the ability of an object to resist changing its motion. So inertia, as you get something moving, say you're pushing someone on a toboggan, or maybe rolling a car, getting it that's stalled, getting it off the road. Tough to get it going, but once it's going, you're fine, and hopefully you don't have to stop it because it's pretty tough to change its direction. So what's Newton's law in easier terms? Because I hate textbook definitions for the most part because they seem complicated. So an object will remain as is until a force acts on it. All right, so the demonstration I always did in class was I would put a textbook on a desk. Actually, I can draw a 3D desk. Look at that. Pretty fancy, eh? I don't know if it'll stand up. There's the fourth letter. So I put a textbook on the desk and I'd say, okay, let's watch it until it moves. Okay, that textbook that's sitting on the desk will not move because it's quite happy in its current state of motion. And it's not going to change its state of motion unless acted upon, unless I push it off the desk or give it a shove. Excuse me. So an object prefers to stay in its current state of motion. Think of when you're driving a car. Okay, so let's do a top view here of the front seat. All right, so here's person X and here's person Y. So stage one. Go around the curve. So what happens to you if you go around a curve in that direction? And you're going fast, the way you normally drive probably. Okay? So let's say it's a bench seat, the old bench seats, you don't have the nice buckets anymore. Person Y slides and gets squished up against that window. And even you as the driver, you'll feel your seat belt sliding, and you move this way in the car. Well, why is that? Well, your bodies want to keep going straight. Okay. Oops. They don't want to go around the curve because they're quite happy in the direction they were heading. So your bodies, if this is the curve, your bodies still want to go straight forward in that direction. As soon as you go around a curve, your car goes around the curve, anything inside is going to roll to the outside of your car. So anything in the back or on your dash or anything on the floor, excuse me, is going to roll to that side of the car, and that's because they don't want it wants to continue going straight on its path. So that's how inertia works. Newton's second law. So I got to add some vector symbols in there for me. So there's his law, and his law is simply FU ma. Okay? Didn't hear that? I said FU ma. So unbalanced force is equal to mass times acceleration. All right, that's what unbalanced force is, and that's what Newton's second law is. Any unbalanced force causes an object to accelerate. So let's talk about the units over here for a second. Yesterday I said that force is measured in newtons, okay? Force is equal to newtons. So what is a newton? Well, based on his second law, FU ma, mass is measured in kilograms multiplied by acceleration from our first unit is meters per second squared. So therefore, a newton is equal to a kilogram dot meter per second squared. Okay? So that's what a newton is. It's mass times your acceleration That's a newton. All right. So some examples. What is the acceleration when an unbalanced force of 50 newtons each is applied to a 40 kilogram person? So, we are dealing with Newton's second law. So we have Fu ma. We know the unbalanced force is 50 newtons. Okay, so that may be applied to the bike, the wagon, whatever the person's in. It's a 40 kilogram person, and we're looking for acceleration. Going back to grade 9 math, we have to get acceleration by itself. We divide both sides by 40, and we get 1.25 meters per second squared is your acceleration. So therefore, the acceleration is 1.25 meters per second squared. Okay. Now, that first law that we were talking about, there's no math involved with it. There'll be some concept questions. There's no equations. Newton's second law has equations tied or linked to it. Second example, a student is bowling with her friends. She gives a 7 kilogram ball an acceleration of 5 meters per second squared. So she really flung that thing. What's the net force on the ball? So how hard did she throw that ball? So Fu equals ma. All right. We're looking for unbalanced force, so it's our unknown. We know the mass of the bowling ball was 7. We know the acceleration was 5. So she applied 35 newtons of force forward when she threw that ball. So therefore, 35 newtons forward were applied. All right, so that's how much force she gave the bowling ball. Third example. So a driver and his motorcycle have a combined mass of 280 kilograms. So we know mass is 280 kilograms. They accelerate from 7 meters per second. Now, you gotta be careful here. It does say accelerate, but that is not a unit of acceleration. Meters per second is a velocity. So V1 is 7 meters per second. V2, final velocity, is 34 meters per second. And they give us a time. So some people will see this already and not like where it's going. What is the net force on the driver and the motorcycle? Well, net force is your unbalanced force, Fu, equals ma, ma. We're looking for Fu. We know the mass is 280. We don't know acceleration, so we have to find acceleration. How am I going to find acceleration? Well, this information comes from our kinematics from our last unit. So we're going to have to go back, use cheat sheet number 1 from the first unit there, and find a formula that uses those values and gives us A, because we really want to know our acceleration. So we find that V2 equals V1 plus A delta T. So a bit of a blast from the past here. 34 equals 7 plus A times 4.2. Subtract 7 from both sides. That would give me 27 equals 4.2A. Divide both sides by 4.2. And that will tell me my acceleration then is equal to about 6.4 meters per second squared forward. So the reason this question is challenging is because it's a two-step question. So now I can take that information back and put it in here, 6.4, and I can get my unbalanced force then to be about 1,800 newtons forward. So therefore, force was 1,800 newtons. So that means the engine generated 1,800 newtons of force to perform this particular acceleration. Okay, determine the missing quantities here. So you might get pictures where you need to find the net force acting here. So my unbalanced force, you can think of it this way. To the right is positive, to the left is negative. So when we want to find our unbalanced force, the 200 will be positive because it's facing right. The 50 is positive, and the 170 will be a negative because it's heading to the left. So when we do that, we can then just add it up and remember which direction's which here. So gives me 30, should be about 80 newtons, and it's a positive answer. So that means that it is to the right. Okay, so there's my unbalanced force. So I just did that by adding up forces 1, 2, and 3. Okay, and you just got to be careful of the signs. To find the acceleration, Fu equals ma. So we know the unbalanced force is 80. We know the mass is 200 A. So acceleration equals 80 divided by 200 meters per second squared. And you can, if you want, you can bring that down to a decimal. So 8 over 20, the 0.4 meters per second squared roughly. And it is to the right. So it is important that we put a direction on there. Okay. Second example, 75 newtons up, force due to gravity. We want to find the unbalanced force. So in order to find the unbalanced force, I need to find the force due to gravity. So force due to gravity is going to be mg. All right, so unbalanced force is equal to ma. Now in the situation with gravity, it's mass times the gravity here on Earth. So that means that Fg is going to be 25 kilograms times 9.81. So 25 times the 9.81 gives us 245.3 newtons. That's going to be down. Okay. So to find unbalanced force is going to equal force due to gravity minus the force up, I guess, or force of air. So 245.3 minus 75, so I'm subtracting that other one off. So that means that I'm falling down with a force due to gravity of 170.3 newtons. All right. Now I want to find the acceleration. Well, I don't have to. The acceleration, your true acceleration, is then governed by Fu ma. All right, it's not 9.81 because we have a resisted force slowing us up. So 170.3 equals, what was my mass again? 25 times our acceleration. Divide both sides by 25. And we get 6.81. All right, so gravity on Earth is 9.81. So anytime you have any air resistance, you are decreasing that gravitational acceleration. So you've slowed from 9.81 down to 6.81. So you've basically taken 2 meters per second squared away from your falling velocity. All right. So I'm going to talk about Newton's third law. I'll tie it up in the next video so I'm not cramming it in. It'll be a short one, and we'll finish up then.